Welcome to position versus time graphs. So we've been working on looking at speed, velocity, and average velocity. So we're going to take a look at position versus time graphs, and this is in relation to their speed and their velocity as well. So we're just going to have to figure out how to read these graphs and to be able to calculate velocity based upon the information that's in the graph. So here at the top it says the position of a football player is given by the graph. And we're going to answer the following questions, making sure to show all relevant calculations and units. So this is position versus time. So first of all, I want to make you familiar with the graph itself. So if you notice here along this side of the graph that says position D in meters and going west, this is called the y-axis. So we're going to label that up here, y. And down here on the bottom, this is the x-axis, and this is the time in seconds. And we're going to label that x. So just to give you a heads up, whenever you're dealing with graphs, if anything is time, it's always going to be on the x-axis. And you can see here that everything is in intervals. So the position here in distance, which is meters, we're going up by 5. So 0, 5, 10, 15, 20, blah, 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 all the way to 100. And here from on this x-axis here, we're going by 3. So 0, 3, 6, 9, 12, la, 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 all the way to 60. And where they both converge here at this point, this is point 0. So we are going to use this graph in order to determine the position of the football player. So as we go further this way, that means we're going further west. So just to give you a hint, if we're going up on the graph, we're going further west. If we're coming down on the graph, we're going to go further east. So we're going to take a look at the first part here. It says, during what time intervals is the football player stopped? So when we take a look at the graph, when you're not moving, that means that you're at a state of rest. So that means there's no motion and no distance that's being accumulated. But time is being accumulated. So as this is our example, and I'm teaching you how to read the graph, I'm going to show you what a time interval looks like when a player in this position is stopped. For instance, right here, you see this plateau, this flat line. So that means that distance is not being accumulated, but time is being accumulated. So we're going to identify the time intervals in which the football player is being stopped. So here we look. So between time intervals 3 and 6, that the football player is stopped, not moving. So between 3 and 6 seconds. So here's one flat area. So here's another flat area. So between 12 and 15. Seconds. Another flat area way down here between 24 and 27. Seconds. Another one between these two, so we've got 42 and 48. Seconds. And then our last one down here, 54 and 57, between those ones. And I'm going to have to like jam that in over here. So 54 and 57 seconds. So all of these time intervals represent that the football player is not moving. He's not accumulating any distance, but he is accumulating time. So when you take a look at the graph, accumulating distance means that the graph is moving up or down. But if nothing's happening in terms of distance, then that means that time is moving left, or moving to the right, sorry. Number 2, it says, when is the velocity at a maximum? East. So remember when I said that here on the graph is when we're moving west So the position, distance, meters in the movement of west. So if we're moving up on the graph, that means we're moving west, but if we're moving down on the graph, that means we're moving east. So when is the velocity at a maximum? In the eastern direction. So we take a look at our graph. Here we're moving up, here we're moving up, but then all of a sudden we're moving down, and then we hit our maximum, which is right here. So when is the velocity at a maximum? So we're going to indicate between 24 and 27 seconds. And it's not the only time that it reaches a maximum, but it's also at 54 and 57 seconds. Now it asks, what is the velocity for the entire trip? Now, we're not too sure yet, so we're going to have to figure that out using the information that's placed before us. So, if we remember from our formulas at the beginning, when we're talking about velocity, we talk about change in distance. And here we have to talk about the entire trip. So, we have to look at the beginning velocity and the final velocity. So, when we're determining the change in the total distance, so total distance, d, we have to look at the final distance, which is d2, minus the beginning distance, which is d1. So let's look here on our graph. So our final distance is way over here. So if we check on our graph and we see where it's at, so our final distance is 10 meters. 10 meters minus what our beginning distance was. Well, that was 0 meters. 0 meters. So it's our total distance is 10 meters that we're going to be working with. So we're going to take our total distance in order to determine what our velocity is. So I'm just going to move this over just a little bit so I've got some room to write. But we also need to know our total time. So if you take a look at the bottom of the graph, the total time was 60 seconds. So we already have that determined just by the graph itself. So we're going to take our velocity that we're going to figure out equals total distance divided by total time. So it equals the 10 meters that we just calculated over the 60 seconds that we know from the graph. So 10 meters divided by 60, figure that out in your calculator, and you're going to get 0.17 meters per second. And because we're moving, and you're going to see on our final here, we're moving west. So we have to indicate that it's west. So in our final here, it's moving up. That means we're moving west. If it was moving down like it is here, that meant that we would have been moving east. Okay, I'm just going to move this up a little bit. I'm going to be moving it back and forth, so that way we can see our little graph here. So what is the speed for the entire trip? So we're going to determine speed. So speed is just speed equals d over t. Pretty straightforward. So we need to know what the distance is covered by the entire trip. So we have to take a look at our graph here. So we're just looking at the total distance. So follow along. You may want to use a calculator in order to keep track of what we're adding here. And I highly recommend this. So our first distance that we're looking at is from 0 to 20. So that's 20 meters plus And then he sits around for a little while. And then he moves again. So from this point to this point. So this is like saying 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70. So from this point to this point is 70 meters. Plus. Then from here all the way down is 90 meters. Plus. From this point to this point is 75 meters. Plus. From this point to this point is still 75 meters. Plus. And from this point to this point is 10 meters. Equals. So this is what you should have been adding. 20 plus 70 plus 90 plus 75 plus 75 plus 10 in order to find the total distance. So if you added it up correctly, you should have gotten 340 meters. And we already know what the total time is because it's 60. So divided by 60 seconds. So you're going to use your calculator, take 340, divide by 60 seconds in order to find out the speed for the entire trip. And so we get 5.67 meters per second. And because this is a speed, it does not have direction. So it's not a velocity. All right. So now we're going to figure out what is the velocity for the first 30 seconds. So on our graph, I'm just going to pull it down. And we're going to look for 30 seconds. So here's our 30-second mark. And we're just going to move our little cursor until it reaches where it intersects. So right here, I'm just going to draw a dot there. I'm going to put it in red. So where it intersects is what a number that we're going to use. So if you look, here's the distance. So it's 15 meters. So we need to determine the velocity. And it's for the first 30 seconds. So first of all, we're going to figure out the velocity between this end distance and then here for the starting distance, which was 0. So total distance equals d2 minus d1. And I apologize that we're kind of jamming this in here. Equals, so d2 is the end distance, and we're saying it's 15 meters. 15 meters. Subtract the starting distance, which was just 0. 0 meters. And 15 minus 0 is still 15, so 15 meters. So because we're figuring out just velocity, so velocity, that's supposed to be an arrow, equals delta D over delta T. And we're going to take our 15 meters over 30 seconds, because that's the point that we were figuring it out on. So 15 divided by 30 gets us 0.5 meters per second. And because we were traveling up, that means we were going west, according to this particular graph. All right. Number 6, it asks us, when is the football player moving west? So when we take a look at the graph, Remember, it says position distance in meters west. As we move up on the graph, that means we're moving west. As we go down on the graph, that means we're moving east. So when is the football player moving west? So we're just looking at time intervals. So between 0 and 3 seconds, they're moving west. Between 6 and 12 seconds, they're moving west. 27 and 42 seconds, they're moving west. And 57 and 60 seconds, they're moving west. So we can record those time intervals down on our piece of paper. So it's between 0 and 3 seconds, between 6 and 12 seconds, between 27 and 42, and then 57 to 60. So now it asks us, when is the football player moving east? That means that they're moving down on the graph. So they're coming down. So between 15 and 24 and 48 and 54. So we record those time intervals. So between 15 and 24 seconds and 48 and 54 seconds. Next question, it asks us, what is the velocity from 12 to 24 seconds? All right, so we're going to move our graph back here. And I'm going to use a different color. I'm going to use blue. So we're going to find out what is the velocity from 12 to 24 seconds. So here's 12 in blue, and here's 24 way over here. So we have to determine what's going on at that point in time. So if this is the final point, because here we're going in time, right? We're going in linear time. This is where the beginning was, and this is where the end point was. Not truly the beginning. Beginning's over here, but in relation to these 2 points that we're talking about, this is the starting point, and this is the finishing point. So that means that this is the beginning distance, and this is the finishing distance. So we're going to find what the total distance is between these 2 points. And we've done that before when we're figuring out velocity. So we're going to have to jam some information in here again. So let's make that look like a triangle. Well, I tried. So we're going to take D2 minus D1. So D2 is where we end up at 24. So if we're looking at the distance here that's being covered at 24, well, there's no distance. It's at 0. And if we're looking at the distance that's covered at D1, then we see that it's 90. So we're taking 0 meters, subtracting 90 meters, and we get negative 90 meters. We're going to keep that negative there. Oh, this is supposed to be attached over here. All right, so we're going to figure out our velocity, which equals delta D over delta T. I'm going to move over a bit here. So now we figured out the distance, so negative 90 meters divided by the time. So between 12 and 24, how much time is that? Well, it's 12 seconds. So 12 seconds. And you're going to do your calculation. Do your division. So just do regular division. What's 90 divided by 12? You can add the negative afterwards. So you type into your calculator 90 divided by 12, and we get negative 7.5 meters per second. And because it's moving down on the graph, that means that they're moving east. Now it asks us for the next question, for number 9, what is the velocity from 27 to 51 seconds? So we're going to look from 27 to 51 seconds. I'm going to change the color. Here's 27 seconds, it's in green. And we're looking at 51, and we're going to use it where it intersects the line. And just like we did with the last one, we're going to determine which one's D1 and D2. Well, because time is linear, this is going to be D1, and this one's D2. This is where we end up. This is where we started from. Okay, I'm just going to move it over so we can show our work here. So we're setting it up the same way as the last question. So D2 is the 35 meters mark. Subtract 0 meters. Because at 27 seconds, he's not going anywhere. And at 51 seconds, he's going 35 meters. So we're going to subtract those two, and we get 35 meters. We're going to solve for our velocity. So 35 meters over what the time is. So from 27 seconds to 51 seconds, you have to figure out how much that is. If you figured it out already, if not, I've got it here for you. It's 24 seconds. So now you're going to divide. What's 35 divided by 24? Punch that into your calculator. You're going to find it's 1.46 meters per second. And because they are moving up on the graph, that means that they are moving west in this case. All right. Last part here. It says, when is the velocity at a maximum? W. When has it reached its full height and it's moved the furthest west that it possibly can? So we take a look at our graph, and the furthest west that we have here is way up here. This is as far west as it can. So between what intervals, time intervals, so between 12 and 15 is when it has moved furthest west. So we're going to figure out when is the velocity at maximum. Well, we don't have to figure it out, but so it's between the time intervals of 12 and 15 seconds. That's it. Now, if I'm going to describe this graph of this football player, this is kind of how I would describe it, just by looking at the information. I'm not worried about calculations or anything. This is a description. So the football player is getting ready to run his first down. And then all of a sudden, the ball is thrown. That means our football player, who knows what he is in the lineup, and he runs for about 20 meters until, who knows? It was a foul, the ball hit the ground, who knows? Then he stops. So he stops for about 3 seconds. And in between the 3 seconds, they might get ready for their second down. He's getting ready. Then all of a sudden the ball is thrown, and now he just hammers it. He's running, and he runs really, really fast during that time. And he's running for 70 meters. He must have the ball, or he's blocking someone from catching that ball. Then whatever happens, somebody drops it, or maybe it was a touchdown, who knows. Then he stops. And he's resting there for 3 seconds, between 12 and 15. No movement. And remember, he's traveling west, so he's gone as far west as he can. Maybe by this time, maybe it wasn't second down, maybe it's now in the other guy's hands, who knows. So now at this point in time in the game, things are different. Ball is thrown. Now he's got to hammer it. He's going to run like you wouldn't believe, and he's running for 90 meters in an easterly direction. So he's running for 90 meters, then all of a sudden he has to stop. And he rests for 3 seconds. That's why there's no accumulation of distance. Then, guess the ball's thrown or kicked or who knows at this point in time. And he runs again for about 75 meters in a westerly direction. And now at this point in time, he stops and he's waiting for 6 seconds. There's no accumulation of distance. Then, ball is thrown again or kicked, who knows. Now he's just hammering it for 75 meters in an easterly direction. He rests for 3 seconds. And then he runs again for about 10 seconds. Maybe they're going off the field. Or 10 meters, sorry. Maybe they're going off the field. So this is just a verbal description of what could possibly going on with this football player during this game. And when you're describing a graph, try to make it so that way it makes sense to what's going on in the graph itself. All right, so we're going to flip to our next page here so you can take a look at it. So we are still doing another position versus time for our mouse. And we're just going to label our axes. So this is Y. And this one over here is X. If you notice here on our Y-axis, it is the position and distance in meters, and you're traveling west. So the further that you're going west. So if you're going up on the graph, you're going west. If you're coming down on the graph, you're going east. So here on this particular line, this axis, this is your time. And your time is in seconds. So it goes from 0 all the way to 100 seconds. And you notice that it's in increments of 5. This one is also, or actually this one's in increments of 25. So this one is very much set up the same way as the graph that we did together. So I want you to use the example that we did together to help you do this particular graph as best as you possibly can. Use colored pens if you need to in order to keep track of the different spots, especially if you're going to be looking at different velocities at different time intervals. And if you're needing help, please let us know. We will definitely come around to help you. There's adults in the room that can help you all the time. Also, if you're at home and you're doing this and you're not sure, I want you can email me, you can message me on Teams, you can send me a quick text, and I'll try and help you out as best as I possibly can. If you find that you don't have enough room to do all your work on these little lines, and it's a good possibility that you don't, feel free to use a piece of loose leaf. I do highly encourage that. Okay, so right now, that's your only job to do, is to do this particular page as your assignment. I'll give you time in class, and then we'll come back at it, and then we'll take a look at it together. All right, I will talk to you soon.